In example 2, we're asked to graph and analyze h of x is equal to log base 2 of x minus 1, and then the minus 3 is away from the logarithm. It's a really good idea to use parentheses here. As a matter of fact, if you didn't, it would be fairly difficult to figure out, are we supposed to add -1 and -3 together and then make that part of the log or not? So you're going to want to go ahead and use parentheses if you want that variable or that number to be included in the logarithm. If we just do a quick sketch of what we think this thing might look like, let me give you a quick sketch here of just a basic like log base 2 of x. And what that's going to look like is this. There's a special point right here, and this is going to be, we'll just say y is equal to log base 2 of x. And so this point right here is 0, 1. If we look at our equation though, we've got some other things happening here, and you can see that there's a shift right by 1 and down by 3. So in our graph, this point is going to be shifted right 1 and down 3. So our graph is going to look maybe something like that. If you want to figure out some exact points, it's often a nice thing to do, especially with these logarithmic equations. We can go ahead and solve for x, and that will help us with an exponential equation. So if we do that, we've got y, you can just replace h of x in this case with y, is equal to log base 2 of x minus 1 minus 3. We want to solve for this log here, so we need to add 3 first. Then we've got log base 2 of x minus 1 is equal to y plus 3. At this stage of the game, we want to change this into an exponential, so we've got 2 y to the y plus 3 is equal to x minus 1. So the base is 2, the exponent, remember we're always solving for the exponent when we have a logarithmic equation, that's y plus 3, and then x minus 1 is the argument position, and that goes to the other side. We could also then add 1 to each side, so we would have 2 to the y plus 3 plus 1 is equal to x. If we try to make a t-chart here, we can definitely do that. We can do an x, and then we'll do h of x or y, either way. This y is really h of x, but we could use y if you want to. And we need to pick some good values here for y that are going to make this easy to deal with. There's a bunch of them that you could pick. One thing that you could start with is -4. I'm choosing -4 because -4 will make this whole exponent here -1. You could also do -5. If you wanted to start off there, you could. But I don't think we're going to need too many points to plot this. We kind of already know what the shape of this is going to look like. So if we choose -4 here, -4 plus 3 is -1. 2 to the -1 is 1/2. 1/2 plus 1 is 1.5. If we look at another nice value to use for y in this case, it might be -3. -3 plus 3 is 0. 2 to the 0 power is 1. 1 plus 1 is 2. So we can build some representative points that will help us to graph this a little bit more accurately. Maybe we'll do just a couple more. So -2 plus 3 is 1. 2 to the first is 2, and 2 plus 1 is 3. -1 here for y, that would be 2 squared. 2 squared is 4, plus 1 is 5. So let's plot these and see if it looks something like we think it might. So we're going to go right 1.5 and down 4. Right 1.5 and down 4. And then 2, -3 would be here. 3, -2 would be this position, and this one is 5 and -1. And so you can see it kind of looks like this a little bit. This edge is a little bit more curved. We just kind of did a little sketch here, what we think it might look like, but plotting some representative points can really help us. It's important to also note that this shift is right 1, which means that the vertical asymptote will shift over 1. So we don't want to go past this line. If you want to, you can draw that asymptote in there as kind of a helper line. And let me use a different color here, we'll use orange. And so this is our helper line here. You can either do it very lightly, in pencil, or use little dash lines. Remember that the asymptote is not part of the graph, but it is a helper line. And this helper line can help us to keep the actual graph a little bit more in line. So we can extend this down here. Now, a word of caution, if you decide that you're going to check this in your calculator, some calculators will not graph this other part right here because they're pixelated. So the calculator doesn't know whether to fill in these little dots here or pixels or not. And actually for logarithms, a lot of times it will choose to not fill these in even though the graph does exist here. So please don't rely on your calculator. Be a better math student and a good thinker and understand that this graph does continue down in this direction. We could make x arbitrarily close to 1, like 1.001, and this graph would just be more and more negative in the y direction if that happened. If we want to analyze this graph, then we can find out a few things. One thing we said we could figure out was our asymptote. So our asymptote in this case is x is equal to 1. In a normal logarithmic function without any shifts, it would be x is equal to 0, and you can see that we're shifting to the right one. Remember to do the opposite of the sign that's there. And so the asymptote will also shift right 1. For the domain, those are all the possible values of x. We can see that the graph doesn't exist for any value that's 1 or lower than 1. So we don't want to include 1, but that is where we need to start. And then we're going to go to infinity. For the range then, actually the graph in green here, any value of y is possible. And you can see also that in when we change this log form into an exponential, that the exponent position really could be just about, you can pick any number you really want to, any real number would work for this. So we can write negative infinity to infinity in interval notation.